So sometimes drawing Lewis structures for polyatomic ions or for molecules can get a little bit complicated because we have some choices to make and there is more than one correct way of doing things. So let's just have a look at a few sort of complicated examples of Lewis structures. The first example that I'm going to give is related to what is known as an allotrope of oxygen. So allotropes are different molecular forms of an element. So good examples of this is that there are more than one form of carbon. So for example, there's familiar carbon in its most common form is graphite. That is pure carbon. But there is also carbon in a less common form, which is known as diamond. And diamond is pure carbon. So diamond and graphite are allotropes of the element carbon. Normally there's one much more commonly found form, which in this case, as you probably are aware on the basis of price, is graphite. So ozone is an allotrope of oxygen. Ozone is O3. And the most common form of oxygen is O2. Ozone is a less common form of oxygen. And we see ozone being produced in high energy environments. So a good example would be in lightning storms. So you sometimes get a characteristic smell of sort of like electricity. That's ozone. And then also the other high energy environment where we see ozone being formed is where we have a lot of UV radiation, which is very energetic light. That's light with a smaller wavelength than violet. And we see a lot of that in the upper atmosphere. And so what happens is when there's a lightning strike or we have really high intensity light, O2 molecules get broken apart into individual oxygen atoms, and then they combine with O2 molecules to make the ozone molecule. So we're going to go through and draw the Lewis structure of ozone and see how it's a little more complicated than what we've seen previously. So I'm also going to want to point out that ozone does form in the lower atmosphere as a result of human activities, and in particular the combustion of fuel in automobiles and also the combustion of fuel in power stations. And O3, it's often used as a cleaning agent. It's quite a potent cleaner. But it's also a really strong respiratory irritant. It tends to kind of make you like gag if you get a lungful of it. And you might have experienced that if you've ever been, in a room where there's like a lot of like sparking going on. This is often like produced by photocopiers and stuff like that. That kind of characteristically like electricity kind of taste and smell. And so O3 can be really irritating to your lungs, particularly if you have asthma or something else. And it also can bleach the leaves on plants, and it causes all sorts of problems. So it's good at the top of the atmosphere, but where it protects us from UV radiation, but it's bad in the lower levels of the atmosphere where we live. So we want, or there exists a nice layer of ozone in the upper atmosphere, which protects us from UV radiation, which is damaging to our DNA. It can break the bonds in our DNA and cause skin cancers. But we don't want ozone down the bottom here where we're living, because it's going to kind of irritate our lungs and kill all our plants and make us sick. So we have this kind of problem. We want ozone at the top but none at the bottom, and human activities have affected both of these things. There used to be a nice big hole in the ozone layer above the South Pole, and some chemists figured out what was going on and what was causing this. And you might have heard there's this thing called the polar vortex, where gases and cold air get trapped above the poles. And what was happening was ozone depleting chemicals was getting trapped above the southern pole, and that was causing it to a hole in the ozone layer would appear every year, and it was a significant hole, and it was extending as far as to places in South America and Australia. And chemists realized what was happening, what was going on, and they banned the chemicals that were responsible for burning this hole. And as a result, the ozone hole is getting better. So those chemists won a Nobel Prize for their work, and it was a real kind of great example of how when people listened to scientists about what was happening on our planet, and then they acted upon that information, that the problem got fixed with pretty much like minimal inconvenience to everybody involved. No one really misses the fact that they can't use particular chemicals in spray cans that they used to be able to use, you know. And so we were pretty much burning a hole in our ozone layer for no good reason. We have similar, you know, debates going on at the moment with the use of fossil fuels. Scientists are definitely encouraging people to move away from the use of fossil fuels. And unfortunately, unlike you know what happened with preventing the hole in the ozone layer, people haven't listened as much. So we're working through that process at the moment. So drawing the structure of ozone, we've got 3 oxygen atoms, and each oxygen atom is in group 6, so we've got a total of 18 electrons. Now, it's really easy to decide what one's going to be the central atom because every atom is the same, so it has to be oxygen, right? And then the 2 outer oxygen atoms have to be connected via single bonds, and each of those bonds consumes 2 electrons. So we've got 18 electrons total, and then we're going to take away 4 electrons for the 2 single bonds. So that leaves 14 electrons left. What we do now is we complete the octets on our outer atoms. And doing that consumes 12 of our electrons, leaving 2 remaining. So what do we do with the 2 remaining electrons? We place them on our central atom. So here we are at this point. Once we get to there, we have 0 electrons remaining. So now all we have to do is check the whether our central atom has an octet or not. So we've got 2, 4, 6. It doesn't have an octet. We're missing 2 electrons. So we have to turn 2 electrons from the outer atoms from being a lone pair to being a bond. So I'm going to move in these guys that are on the right here, there we go, and put a double bond here. And now you can see we have the correct number of electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. So the electron count is good. And then we have to check the octets, right? So we've got the oxygen on the left, 2, 4, 6, 8. That is correct. We have the central oxygen, so the one with an atom attached to either side, 2, 4, 6, 8, because it's got 2 bonds there. So that is correct. And then this oxygen out here, and it's got, so we want to, maybe we can just put them as being like that. 2, 4, 6, 8. There we go. And so he's correct as well. So everything looks good. All the electron count is good, and all of the atoms have an octet. So this is a good Lewis structure. The thing that makes it a complex Lewis structure is the fact that why did we pick this particular oxygen atom to bring the lone pairs in from? Couldn't we have picked the other one equally as validly? Couldn't we have picked this one and brought these guys in? So in the final step there are 2 choices, right? We can bring the lone pair in from the right, or we could bring the lone pair in from the left. And this would give us 2 valid Lewis structures. So is one better than the other? Does it matter? What's going on here? What is the real structure? Do we really have 1 single bond in ozone and 1 double bond? Are there really 2 different kinds of bonds here? Well, when you look experimentally at the structure of ozone and you measure those bonds, you find that both of the bonds are exactly the same length, which indicates that there isn't 2 different types of bonds, right? Because what we're saying is both of the bonds in ozone are the same. And what we find, how we can explain this, is that we need to consider that in the real structure of ozone, it's actually an average of the 2 correct Lewis structures. So the correct structure is actually an average of the 2 Lewis structures. It's actually what we call a resonance hybrid. So it's not that it's flipping between one form and the other, because if it was, we'd still find two different types of bonds, it's literally an average of the two, right? So if you have a mixed breed dog, say it's like Chihuahua with Great Dane, it's not like Chihuahua 1 minute, Great Dane the next, Chihuahua, Great Dane, getting bigger, smaller. That's not what's happening. It's a mixture of both of those things at any one point in time. So how we indicate that our molecule is a resonance hybrid of more than one structure is we draw out all of the correct Lewis structures and we separate them with a double-headed arrow. So sometimes we have to draw more than one picture in order to illustrate the bonding in our molecule, and then we separate those diagrams using the double-headed arrow. So we'll have a look. So that's our first kind of example of a complex Lewis structure. The other example of a complex Lewis structure is when we have a polyatomic ion. And we talked a little bit about this in the last video. So if our species has a charge, then you have to add electrons if it's an anion equal to the charge, or subtract electrons equal to the charge if it's a cation. So if I have this polyatomic cation ammonium ion, the ammonium ion NH4+, nitrogen is in group 5A, contributes 5 valence electrons. There are 4 hydrogen atoms, each of which is in group 1A, and then because there's a positive charge, I've got to take away 1 electron. And so that gives me 5 plus 4, that would give me 9, minus 1, this guy has 8 valence electrons. So when I do that first step of adding up the valence electrons, I have to either add or subtract electrons equal to the charge. So here's nitrate, it's got a -1 charge, so that means I'm going to add 1 electron into the electron count. So again, I got 5 electrons for the nitrogen because nitrogen's in group 5A. I've got 3 oxygen atoms and they're in group 6A, but then here's the kicker, I add in an extra electron to take into account for the -1 charge. So 5 plus 18 gives me 23, plus another electron gives me 24 valence electrons. So that's it, right? So we've got to take that into account before we start doing the rest of the Lewis structure. We have to add up the valence electrons correctly. Okay, so that's our second example of a complex Lewis structure. So let's go through it and do the whole thing. We're going to draw the Lewis structure of the nitrate anion. We've already done this step. We get 5 electrons for the nitrogen, and then with 3 times 6 for the oxygens, because oxygen is in group 6A, and then we have to add in 1 electron for the negative charge. So 5 plus 18 gives me 23, plus 1 gives me 24 electrons. So what atom goes in the middle, what atoms go on the outside? Nitrogen's in group 5A, oxygen's in group 6A, the one with the lower group number goes in the middle. So I'm going to put my nitrogen in the middle and then my 3 oxygens around the outside. Now, before I get too carried away, I always put a polyatomic ion in parentheses with the charge outside those parentheses. Now the outer atoms need to be connected to the central atom by at least single bonds, so I can go ahead and put those in, and then each of the single bonds consumes 2 electrons. So 3 of them, each using up 2 electrons, so 24 minus 6, 18 electrons left to finish everything else off. So my next step is going to be to complete the octets on my outer atoms. So at the moment, every oxygen atom has 2 electrons around it, so I'm going to be putting another 6 electrons as lone pairs on each oxygen atom. There they go. Right? Okay, so 3 lots of 6 electrons leaves 0 electrons remaining. So I went ahead and did that. So then at this point, I'm here, right? And so what my next step is put any leftover electrons on my central atom. There aren't any, so that's not needed. And then my final step is I need to check that my central atom has an octet, and if it doesn't, convert lone pairs to bonds until it does. So when I check my central atom here, there are 6 electrons around it. So I've got to add in 2 electrons and make 1 double bond. And there are 3 possible ways of doing this. So in order to be correct, I have to draw out 1 Lewis structure for each of these possibilities and then separate them by the double-headed arrows, right? So this is one resonance structure, this is another, this is another. In reality, it exists as a hybrid of all 3. So it's pretty complex, right? That's why this section is called complex Lewis structures. Okay, cool. So here we go. Here's another one. It says, draw the Lewis structure for the sulfur trioxide molecule. Be sure to include all resonance structures that satisfy the octet rule. So sulfur is over here and oxygen is over here. So they're both in the same group. They're both in group 6A. So 6 electrons for the sulfur and then 3 times 6 electrons for the oxygen gives me a total of 24 electrons. Now they're both in group 6, but remember we said the central atom will be the one that is lower down in the group if they're in the same group. So our central atom is going to be sulfur, and then we have our 3 oxygens attached. So that means we're going to use up 6 electrons, 2 electrons for each bond, in order to get the oxygens attached. So now I've got 18 electrons left to finish everything off. So now I'm going to put those electrons that remain as lone pairs on the outer oxygens in order to give every oxygen an octet. There we go. So now every oxygen has an octet, and that used up all of my remaining oxygens. So step 5 is not needed. I don't have to put any leftover electrons on my central atom. What I've got to do now is check my central atom and see if it has an octet, and if it doesn't, I'm going to turn lone pairs on outer atoms into bonds until it does. So my central atom has 2, 4, 6 electrons around it. Okay, so I'm going to have to bring in 2 electrons to get it up to 8. So you can see that there are 3 ways of doing this. I can bring them in from the atom, the oxygen atom that's on the far right. That would give me that. But alternatively, I could have brought them in from the oxygen atom that was on the left. Or there's a third way I could have done that, and that would have been to have brought them in from the oxygen atom that was at the bottom. Now, I want to check at least one of these for my 2 things. What do I need to check for? I need to check for electron count, and I also need to check for octets. So let's check for electron count. So we've got 24 electrons in total in this guy. Let's see what we've got here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So electron count looks good. And then we need to check octets. 2, 4, 6, 8. So that oxygen is good. 2, 4, 6, 8. That oxygen is good. 2, 4, 6, 8. That oxygen is good. And then the central sulfur, 2, 4, 6, 8. So octets are good. So 2 single bonds to the oxygens with 3 lone pairs on those oxygens, and 1 double bond with 2 lone pairs on that oxygen is good. So all 3 of these Lewis structures are pretty good, are definitely good. They all satisfy the octet rule. They all have the correct number of electrons. Okay, so that's our complex Lewis structures. 2 examples that we looked at there. One was where we had resonance, where we had to draw multiple correct Lewis structures separated by arrows. And then the other complex Lewis structure that we looked at was where we had the Lewis structure of a polyatomic ion, where we had to either add or remove electrons equal to the charge, depending on whether we had an anion or a cation, respectively. Okay, hope you found the video helpful, and please reach out to me if you need any more assistance.